In this video, I am going to talk about measurements and uncertainties associated with measurements. During our day-to-day activities and scientific experiments, we make many different kinds of measurements. They could be volume of liquids, weight of objects, length, pressure, temperature, and so on. One must be aware that every measurement is associated with uncertainty. Reporting of any measurement is not scientifically correct without reporting the uncertainty associated with it. In our day-to-day activities, we ignore them, but uncertainties are there. Scientifically, it matters and can be very crucial to the correct interpretation of the results derived out of experiments. Just to motivate you to start thinking about it, let me begin by posing this question. I have a pencil and I am interested in its length. I give this pencil to 3 individuals and ask them to measure the length and report. I receive 3 different kinds of measurements: 8, 8.2 and 8.22. To keep it simple, I have purposely omitted the uncertainty discussion here, which anyway we will discuss a little later. But what you have now is that the length of the same pencil has been reported in different ways. They could all be wrong if they have not done and reported the measurement correctly. But then all the reported measurements could be correct. Why? Hopefully by the end of the video, you will be able to understand the concept. So let's look at how to go about measuring the length of any object. In our example, we will measure the length of an arrow with a standard ruler. In that process, we will also deal with the idea of uncertainty. Let's put the arrow against the ruler. We will use the centimeter scale. We will align one end of the arrow to 0 and observe the markings on the scale at the other end of the arrow. Grossly, one can readily see that the arrow is between 4 to 5 centimeters. So we can surely write 4 to begin with. Can we do better? Okay, let's blow up this part of the figure. Now you observe that the 1 centimeter distance between 4 and 5 centimeter marks are further divided into 10 equal parts. Therefore, the distance between the adjacent small marks is 0.1 centimeters. So we can refine our measurement now. We observe that the end of the arrow is between, let's see, 4.1, 4.2, 4.3, 4.4, yes, between 4.3 and 4.4 centimeter marks. So now the length is 4.3 for sure and little more than that. But it is definitely not 4.4. This is exactly where you have to now estimate. How much more than 4.3? You may want to call it 4.35. Someone else may see it as 4.33 or even 4.36. It is in the third digit indicated by the arrow where some kind of estimation is happening. You are not certain. Or in other words, this position is doubtful. You see, the doubtful digit is at the level of 1/100th of a centimeter. Another important thing. The smallest division in this scale is 0.1 centimeters. That is 1/10th of a centimeter. And so the uncertainty is 1/10th of the smallest division. The uncertainty in the measurement using this scale is 1/10th of 1/10th of a centimeter. That is 1/100th of a centimeter. Hence it is important to estimate at the level of 100th of a centimeter. That is, in practical terms, you have to place the second digit after the decimal. You may ask, why is that important? One can leave it at 4.3. But no, that is not right. Because by simply saying 4.3, you are not correctly conveying the uncertainty associated with the measurement. That the uncertainty is 0.01 centimeters can only be conveyed when you put down the next digit, which is the doubtful figure, where some kind of estimation is happening. Can we say that the length is 4.334 centimeters? No. Because you do not have further divisions within the smallest division on the scale. So you cannot be certain up to 4.33 so as to make an estimate at the third place after the decimal. So it will only be fair to say that the length of the ruler is 4.33 centimeters plus minus 0.01 centimeters. You may not choose to write plus minus 0.01 centimeters because the measurement itself indicates that the uncertainty is 0.01. Another interesting point. What if the tip of the arrow were to visibly align with the third mark after 4? Here again, simply leaving it at 4.3 will not be right. You have to put down the digit corresponding to the hundredth of a centimeter. That is, you have to put down some digit after 4.3. So you have to report it as 4.30. What if we had a different ruler, as shown in the figure? How would you record the measurement? It is certainly between 4 and 5 centimeters. So we begin by putting down 4. How much more than 4? You have to make an estimate. But to what level do we estimate? Now in this scale, the smallest division is 1 centimeters. The uncertainty is 1/10 of the smallest division. That is 1/10 of 1 centimeter, which is equal to 0.1 centimeters. So you should put down the estimate at the level of 1/10 of a centimeter. So you should say 4 point something. You may say it as 4.3, or someone may say it as 4.2, or maybe even 4.4. All is fine as long as you are putting down the digit in the tens place. That is the first place after the decimal. Here again, if the tip of the arrow were to visibly align with the 4 centimeter mark, then we cannot leave it at 4 centimeters. We should say 4.0 centimeters. That way, we convey that the uncertainty is 0.1 centimeters. You may report 4.0 centimeters plus minus 0.1 centimeters in this example. Last example. Maybe you can pause the video and work it out yourself. Feeling lost? Okay, don't worry. Here, the first digit you place itself is an estimate. Why? It's like this. What is the length of the smallest division? 10 centimeters. So, the uncertainty is at the level of 1/10 of 10 centimeters. That is 1 centimeter. So one has to write 4 or 5 or 3, whatever your estimate is. And whatever number you place is itself the doubtful figure. So now you understand why 3 individuals measuring the length of the same pencil can report differently. It is possible if their measuring devices have different resolutions. You can appreciate that as you move from 8 to 8.2 to 8.22, the uncertainties of the devices are different. 1, 0.1 and 0.01 respectively. And the precision of the device increased in the same order. One last note before I end this video. In the first measurement, there is one significant figure. In the second, there are 2 significant figures. And in the third, there are 3 significant figures. Now, in one of my next videos, I will talk to you about significant figures and look at rules that will help you to find out the number of significant figures in a given measurement.